So can we start?
Whether we have all concerned people online?
Good morning, sir.
Vikas,
Good morning, sir.
Yes, sir.
Yes,
Yes.
sir. May I, with your permission, Honorable Sir, may I ask Nishtha to begin, sir, proceedings?
Please go ahead.
Nishtha, please initiate the
Yes.
proceeding.
A very warm and pleasant morning to all the distinguished guests, dignitaries, faculties, and students present here today. I, Nishtha Parashar, and Dr. Ashish Pareta cordially welcome you all to the inaugural session of the International Conference on Recent Advances in Design, Material, and Manufacturing 2025, organized by Department of Mechanical Engineering, Amity School of Engineering Technology, Amity University, Madhya Pradesh. It is our proud privilege and honor to have with us distinguished guest, Professor Dr. Sanjeet Kumar Dwivedi, Senior Consultant in Siemens, Denmark, and also adjunct faculty at IIITM, Gwalior. Professor Dr. P.K. Jain sir, IIITM, Jabalpur, Principal at RJIT Tekanpur, PSF Academy, Gwalior. Honorable Vice Chancellor, Professor Dr. R.S. Tomar sir, directors, HOIs, all the faculty members, participants, attendees, and the students in online mode. I once again welcome all and thank you for sparing your valuable time to be with us today. ICRE DMM 2025 is an international conference that provides a dynamic global platform for researchers, academicians, industry professionals, and innovators to exchange ideas and advancements in the rapidly evolving domain of advances, materials, and manufacturing. The conference features diverse technical tracks, including smart and sustainable materials, advanced manufacturing processes, design and dynamics of mechanical systems, robotics and automation, and data-driven manufacturing technologies. ICRED MM2K25 aims to promote interdisciplinary collaboration, showcase breathtaking and research exploration, and how emerging materials and modern manufacturing technologies are shaping the future of engineering and industrial development. To mark the beginning of the conference, let us take the blessings of Ma Saraswati, Goddess of Knowledge, and fold our hands in prayer. Thank you, everyone. Before we move ahead, we would like to take a moment to felicitate our esteemed guests. Even though we are meeting in a virtual mode, our respect and gratitude remains the same. I respectfully invite our Honorable Vice Chancellor Sir to kindly present flowers bouquet to Professor Dr. Sanjeet Kumar Dwivedi Sir as a token of welcome for the event.
Sanjeevji, welcome to Amity University Gwalior.
Thank you very much, sir. Thank you so much.
Thank you, sir. I request Professor Dr. Vikas Thada sir to graciously present flowers bouquet to our Honorable Vice Chancellor sir.
Welcome, sir.
Thank you.
Thank you, sir. I now request Professor Dr. Anshul Gangili sir to graciously present flowers bouquet to Professor Dr. P.K. Jain sir.
Welcome, Professor P.J. Jain, sir.
Thank you, sir. Thank you, respected dignitaries, for gracing the event. Now, to give us an overview of this prestigious conference and its objectives, I invite Professor Dr. Anshul Gangili, sir, HOD, ME, and convener ICRADMM 2025 to introduce the international conference. Sir, please.
I request, since my director has joined, Professor Vikas Thada, sir, so I request at that particular forum that Professor Vikas Thada, please begin your introductory address. Sir.
Thank you, sir. Distinguished guests for the conference, Honorable Vice Chancellor, sir, the convener and head of the department, ME, Dr. Anshul Gangili, all other HOIs, heads, faculty members, esteemed delegates, distinguished academician, industry professionals, and young innovators. It's an honor and a privilege to inaugurate the second international conference on recent advances in design, materials, and manufacturing, ICRAD 2025, a flagship initiative of the Department of Mechanical Engineering, Amity University, Madhya Pradesh. This conference is not just a calendar event, it's a strategic platform for technological foresight, research convergence, and academic leadership in the evolving domains of advanced manufacturing, material innovations, and digital engineering systems. ICRADMM 2025 showcases a remarkable spectrum of scholarly contributions in the field of mechanical engineering, from multi-scale material modelings, laser-based additive manufacturing, and intelligent process control, to robotics, integrated design, thermal optimization, and in the field of AI, the AI-driven diagnostics. We are proud to host papers that delve into topology optimization and generative design for lightweight structures, high entropy alloys and composite interfaces for aerospace and biomedical applications, digital twins and sensor fusion for predictive maintenance and thorough life engineering, sustainable manufacturing workflows integrating renewable energy and circular economy principles. Other than this, we also have CAD-CAM CAE advancement enabling real-time simulations and validations. The diversity of all different kinds of paper clearly reflects that interdisciplinary and multidisciplinary nature of the modern engineering, where mechanical, electrical, materials, computational sciences, artificial intelligence, machine learning are converging together to solve complex industrial designs or challenges. Despite geographical boundaries, this year's conference has successfully transitioned to a hybrid digital format, enabling real-time online presentations from researchers across India and abroad. And this digital engagement not only democratizes access, but also aligns with the global shift towards virtual collaboration with all delegates in industries and remote innovation ecosystems. It's a testament to our institutional ethos, and I'd like to acknowledge the core organizing team whose technical acumen and leadership have shaped this event. Dr. Anshul Gangle, Dr. Nasir Khan, Dr. Nagin Sharma, Dr. Ashish Pareta, Dr. Nitish Sinha, Dr. Sushil Pandey, and every other faculty members who has directly or indirectly, along with our student volunteers, technical staff who have worked behind the scene to make this event a success. Their effort reflects the department's commitment to precision, innovation, and impact. To all presenters, session chairs, and attendees, I really urge you to engage not just as participant, but as co-creator of future technocrats. Let this conference be a launchpad for joint research proposals across institutions and disciplines, collaborative publications in high-impact journals, industry academia partnerships for translation, research, and technology transfer. Let us move beyond incremental progress and aim for disruptive innovation, the kind that redefines manufacturing paradigms and contributes to national and global development. As he formally inaugurates ICRAD 2025, let us reaffirm our shared commitment to engineering excellence, research integrity, and academic leadership. May this conference inspire bold ideas, foster meaningful collaboration, and accelerate our collective journey towards a smarter, more sustainable manufacturing future. Thank you very much.
Thank you, sir. Thank you so much, sir. Moving forward, before inviting our Honorable Vice Chancellor, Professor Dr. R.S. Tomar, sir, to deliver the opening remark, allow me to present a brief introduction of his esteemed profile. Professor Dr. R.S. Tomar is MSc, MPhil, PhD, FRSB London, FCBWS Hong Kong, FICER, FSLSC, FIASC, and he is Vice Chancellor of the Amity University, Gwalior. He has served as a Vice Chancellor of IES University Bhopal also. He was founding campus head of the Amity Gwalior campus. He was the director head of the Amity Institute of Biotechnology, Dean Life Sciences, and Dean Academics, Amity University, Madhya Pradesh, Gwalior. Professor R.S. Tomar has more than 33 years of teaching, research, and administrative experience in higher education in varied disciplines of science, including life science. Professor Tomar is actively engaged in teaching, research, and innovation. His research interests include nanobiotechnology, microbiology, herbal medicine, cancer biology, animal biotechnology, and environmental biotechnology. He has, to his credit, more than 150 research publications in various national and international journals of repute. He has filed 27 patents, of which 26 has been published in Patent Journal of India. 2 patents has been granted and another 1 are under the process for grant. Professor Tomar has published more than 35 books, chapters published by national and international publishers. Recently, a book entitled Nanobiotechnology, Concept and Application in Health, Agriculture, and Environment, edited by him with co-editor, has been published. He has delivered lectures in more than 75 national and international seminars, symposia, conference, and workshop. He is a member of various national and international scientific bodies and reviewer and editor, national and international journals. Recently, he has been elected as a fellow member of the Royal Society of Biology, London, UK. May I request, sir, for delivering the opening remark, please, sir?
Thank you, Dr. Ashish. The chief guest of today's inaugural session of Second International Conference on Recent Advances in Design, Materials and Manufacturing, that is ICRA DMM2 2025, Professor Dr. Sanjeet Kumar Dwivedi, Senior Consultant, Siemens Gamesa, Denmark. Keynote speaker, Professor Dr. P.K. Zain, Principal RJIT, Tekanpur. Pro-VC Research, Dr. M.P. Kaushik. The organizing committee, headed by Dr. Vikas Tada, the HY Asset, Head of Department, Dr. Anshu Gangele, faculty members, Nishtha, Ashish,
Sir, there is a network issue, so they will log out.
Uh, Sorry for the inconvenience. We are facing a technical issue with the Wi-Fi and internet. Please.
Am I audible to all?
Yes, sir.
Yes, sir.
Sorry for the technical issue. Yes, sir. You're audible, sir. Welcome back, sir.
Sorry for this technical glitch. Happens. Our dependence on technology always teaches some chapters, some lessons like this. So more dependence on technology means more handicappy. Physical presence was much better than this. Anyways, so I welcome you all for this particular conference. And as I was mentioning, that design, materials, and manufacturing, these three aspects are interconnected, interrelated to each other. Any change in one aspect may affect the other one. So you all know that design determines the product's function and its aesthetics, and the material selection impacts the performance and the cost of the material and all the product overall. And then how it has been manufactured, that also plays a very important role in bringing about any product for any purpose, any solution, or any problem that you take up and provide a solution to the problem. The product development cycle is complex, you all know, that involves several stages from ideation and prototyping and finally to manufacturing. So at each stage, there are some specific parameters that must be followed. They need to be more attentive. And the important thing is that the idea that comes first, how we can create a design out of that idea. That is very important. Any design which you think out of any idea may not be fruitful because always anything which you think of cannot be converted into a product. So, how your idea or how this idea can be converted into a particular product, that depends upon the scaling, minimizing the cost, and some other factors also. Because in today's world, we are talking about the Make in India. So, Make in India is going a long way. And I'm very sure that in the next 10 years, we shall be self-sufficient with regard to manufacturing of different kinds of engineering products. Our scientists, our engineers, our academicians, they are working day and night. And in all the domains, government is directly involving itself. The best part is this. Because earlier, government was dependent by providing the some funds to the researchers to ideate and create some design. But nowadays, they have incorporated the industry players also. And that's why these all agencies, funding agencies, they have been pooled into one agency, that is ANRF, Anusandhan National Research Foundation. And I'm sure this particular initiative government is already playing a very important role. It will go a long way. And many products, many ideas will come up and they will convert it into the products. So this ICADMM2 that reflects this reality, that 21st century engineers who are facing challenges for sustainable infrastructure, intelligent manufacturing, and resilient materials. So various kinds of submission we have received for this conference from different parts of the globe, and they are basically designed, not suddenly it has been done. They have been taken into consideration in such a manner that we are focusing on these aspects like design optimization and mechatronic integration, advanced materials for extreme environments, thermal systems and energy modeling, automation, AI, and digital manufacturing frameworks. So such diversity is not incidental. It has been done intentionally so that we can target these problems and we can come up with some idea and the product formation. So the conference like this is the integral of this vision. and they serve as a accelerator for faculty-led innovator clusters, student research incubation, and international academic partnership. MIT is in the forefront in getting the academic partnership with the foreign players, and not only in engineering, various other aspects are also being considered to enter into any memorandum of understanding and to reach to some sort of product formation. So, dear researchers, your work here matters. I am hopeful that it will contribute to larger narrative, set a larger narrative, where India emerges not just as a consumer of technology, but as a creator of knowledge, a driver of innovation, and a leader in sustainable engineering solutions. At MIT University, Madhya Pradesh, we not only teach in the classrooms, just theoretically, we provide them hands-on training also, so that our students are equipped with the knowledge with hands-on training. Our pedagogical model is anchored in research intensity, industry relevance, and global benchmarking. So these are our aspects that we take into consideration. I'm confident that this conference will serve as a pivotal platform for in-depth discussions and knowledge sharing on the latest advances in materials and their future directions in engineering. It is an ecosystem where participants engage in critical thinking, they challenge the existing norms, and co-create innovative solutions, ultimately shaping the field's trajectory. As you formally inaugurate ICA DMM 2 2025, let us reaffirm our shared commitment to academic excellence, technological leadership, and societal impact. May this conference ignite new collaborations, inspire bold thinking, and strengthen our collective resolve to engineer a better world. Here, bold thinking I highlight. Reason being, sometimes we have fear in our minds that this particular thought may not result into a product. No problem. Try it. Until unless you try it, you cannot go to the next level. You all know the history of development of the light bulb, Thomas Alva Edison. He tried 100 types of materials. And finally, he concluded that this particular material, tungsten, is the best one, and that will glow and give the light. So, this much patience you can understand. And patience to this extent that one story is also associated with that when Thomas Alva Edison was going to demonstrate his invention in a conference, his assistant was carrying the bulb with him. And he was about to present it next day. And anyhow, that particular bulb got broken. So he again he tried to make the new bulb, and for the confidence building, he again told his assistant to carry the bulb. This kind of motivation and patience is also very much required. Anybody who's working with you, co-workers, sometimes we think that, oh, he has spoiled my this particular research. You should not come to me now onwards. So this kind of behavior actually create fear in not only your minds, the other minds also. So that particular individual also get affected. So you can understand from the inventions, from the patience, from the perseverance of the innovators all over the world, and we should always go into details of the history. History, not the history of this Akbar Birbal. History of everything is there. If anything starts, reaches to some level, it creates history. So we must try to understand that what kind of innovations have been done so far, what is the requirement of the society, how we can bring about change in that, what is the need of society in future, maybe future after 20 years. Any engineering which you can think of for next 20 years, you can lead the world. Don't think now, okay, now this is the problem, I will solve it, and after 1 or 2 years your innovation or invention will go in vain. You should think of 20 years beyond, and only then you can say whatever you have ideated and created, that will be more and more helpful, fruitful for the future environment. I wish all the best to our Nayash of this committee, that today I would like to see that there are some deliberations coming out with which you can reach to some conclusions, and really you can think of giving the new kind of materials, because India is progressing very fast And this is the time when we need new materials. New materials means new materials not only from their weight point of view, new materials means from their cost effectiveness also, very important. So we have to check that the cost also is checked, and it should be more effective material. So that kind of engineering is required nowadays. I'm not a material scientist, but some of the nanomaterials are developed by our lab also. I was a part of that. And one invention that we have done for the nanogel for the wound healing, that also is small materials created out of zinc, copper, and silver. And that particular preparation is very much effective in the wound healing in diabetic patients. So this is a time of materials. Materials, not only engineering materials, in medical science also they are widely used. You all know that. So again, I wish you all the best. Thank you very much. Jai Hind, Jai Bharat.
Thank you, sir,
Thank
for
you, sir.
providing an inspiring start to the international conference on recent advancement in design, material, and manufacturing 2025. Moving forward, it is my privilege to introduce our distinguished speaker, Professor Dr. Sanjeet Kumar Dwivedi, sir. Professor Dr. Sanjeet Kumar Dwivedi is a fellow of the IET UK and a senior member of the IEEE USA. He is a senior consultant in green energy and power electronic systems with vast experience in converter control, offshore wind applications, and hydrogen integration. His professional journey includes key R&D leadership roles at the Siemens Gamesa Renewable Energy, Everfuel, and Damos Drive. Dr. Dwivedi holds a PhD from IIT Delhi, a gold medal winning master's from IIT Roorkee, and an MSc in Innovation and Business from University of Southern Denmark. He has authored more than 50 technical papers, over 14 international patents, and several books with IEEE Press and IET Press. He currently serves on the board faculty of the University of Southern Denmark, is an adjunct professor at IIITM Gwalior, and contributes as an associate editor of the IEEE Transactions on Industrial Electronics. Its outstanding work has been recognized with prestigious honors, including the IETE Bimal Bose Award and Danfoss Global Innovation Award. We are truly honored to have Dr. Dwivedi sir with us. Respect, sir. We are eager to hear your insightful address. Please grace us with your words.
Thank you very much, Dr. Pareta. Am I audible?
Yes, sir. You are audible.
Okay. So thanks for your kind word. And I welcome all participants, our respected Vice Chancellor, sir, organizer of this conference. And I'm sharing my slide now, and please let me know if you are able to see them. Can you see them?
Yes, sir, it is visible now.
And it is clear, or
Yeah,
it's
exactly.
having obstruction with pictures?
Yes, sir. Yes, sir.
Okay. I will skip my introductory slides, but one thing I need to mention, as Professor Tomar emphasized about product development and the contribution of academia for solving the ideation and the prototyping part and helping industry to commercialize and develop a product where I have this exposure of academia of around 15 years before moving to industry. So I will be very happy after this talk, some practical questions. What is the European ecosystem and how it works, and what is the difference between Indian academia and industry and European industry and academia. So today's topic of my talk is accelerating the green energy transition for Atmanirbhar Bharat through intelligent power converter, digital twin, and hydrogen integration. And in this presentation, I will convince you with my thoughts that if we want to make Atmanirbhar Bharat, then we need to have a means for energy independence. And I will share my logic why I'm saying it. In order to become the world leader, if we are still reliant on fossil fuel, then we are stuck with the world politics and influence of some political powers, which they are not allowing us to become independent. Even though we are having a growing economy and top 4 largest GDP in the world, but this green energy transition is must, and it can be done only through intelligent power, like power converters, digital twins, and hydrogen integration. I will show you my fact why hydrogen is necessary for this energy independence. So I plan this lecture to, we'll see this green energy challenges. Then we'll be deep dive to power converter for energy conversion. That is my core research topic, and which is well related with this energy conversion and green energy transition. Then we'll come to this conference topic. We are having this digital twin for reliability, resilience, and cost reduction. Then we will move to the hydrogen as a flexible energy vector for India. And in the end, we'll see the roadmap opportunity and what we can contribute from the academia. And I will open the forum for the question and answer in the end. So good morning to everybody. And it's a privilege to speak at MIT University Gwalior. You are a part of campus that builds solutions, not excuses. And India will lead the next cycle of engineering growth through skill, science, and speed, and consistent effort of all we academician. And my favorite, punchline, what I see that when knowledge meets action, innovation become inevitable. And everybody is having potential to contribute for this innovation. And I can also give you a reference of your vice chancellor who is in this age contributing for so many patents and so many technologies and so many good ideas. So for all the participants, I will emphasize here that we need action item to innovate and make some tangible product. Why green energy now for Bharat? Uncertainty in the world politics as oil become a strategic tool to influence rapidly growing economics like Bharat. We have seen in last few months, specifically this tariff war and a pressure for purchasing oil from certain suppliers. So this is something we need not to be trapped in this pressure. Rising power demand in industry, mobility, and urban growth. This is something I will show you with the data that today's power generation is around 430 gigawatt for India. And by next 5 years, we want to reach to 1000 gigawatt. And by 2047, when our Atmanirbhar Bharat target is there, then we will reach around 3000 gigawatt power. And for reaching to that power, that is only possible with the green energy transition. Need not to say that air quality, that is something very poor in our metros, and life is miserable. So this also indirectly help us to increase the air quality of not only metro city, but whole country environment. And global climate commitment and competitiveness. COP30, we have seen yesterday, already world agreed to reduce the global average temperature below what is today's below 2 degrees, and that is we are also part of this commitment. And with this green energy transition, we are able to link to the jobs, new manufacturing, and new skills. As I told you, we can see here data that vision for self-reliant India in technology and supply chain. We need to build core technology and we need to secure critical component as well as we need to strengthen domestic supply network and need to domestic design, manufacturing and intellectual property. And that is done that it is needed energy security and need ownership. And when you design and manufacture in India, you control quality, cost, and timeline. You reduce exposure to foreign restrictions. And IP created inside the country build long-term strategic strength. It also attract investment because partners see India as a creator, not only a buyer. Role of standard testing lab and local ecosystem where academia can fill this gap and take a lead. So we cannot leave this part for the industry. So they should contribute for that. They should, otherwise if academia will not take lead here, then industry will take their own role for making these standard. As well as these testing lab, we can accelerate this manufacturing and we can accelerate this green energy transition through sustainable solution. We can add, value proposition to reduce this green hydrogen cost, and we can create our own local ecosystem also. So this strong norms of safety and performance, standard being order and trust to fast growing sectors and testing lab inside the country to reduce delay and cost. And here on the right side, you can see what is our power generation. Now we are here in between around 450 gigawatt. And then if you see the right side, that this is the exponential growth until 2047 or 2050. And in the downside, you see the contribution from different energy sector. And top one is from the offshore wind, onshore wind, our solar power and biomass power. So we need to do a lot because these data are from the Government of India Power Ministry side. So this is a Government of India committed for this exponential growth, and we are so far we are doing above than the world average. Our 60% energy generation is through green power, and that is remarkable. So when I'm saying energy transition and green energy transition, why hydrogen matter? We know that renewable energy output fluctuate. And this fluctuation that can be smoothened by, because hydrogen absorbs the surplus that the grid cannot accept. You can argue that hydrogen absorb, battery can also absorb, but in order to smoothen this 1,000 gigawatt of energy, you need a huge investment on this battery infrastructure, and that is not a practical solution. But using type 4 hydrogen cylinder and storing the molecule for forever, that is a practical solution. And hydrogen support long duration storage with weekly and seasonal capability, which is not possible with the battery. And then most important, heavy industries that need high temperature heat, which electricity cannot provide easily. So storing energy, electrical energy cannot be a solution for the heavy industries. I will come to this part later and explain it further. So hydrogen fill the gap. It also acts as feedstock for chemicals, as a fuel, and hydrogen enable decarbonization of power sector and for the industry. There is a common question. We sometimes we say green hydrogen, sometimes we say pink hydrogen, sometimes we say gray hydrogen. So there is a green hydrogen uses renewables, and then if hydrogen color is blue, then it means it is uses fossil fuel, but carbon is captured and storage. If it is a gray hydrogen, then it is uses fossil fuel and specifically gas, natural gas, but it is not capturing the carbon. carbon is emitted, carbon dioxide is emitted to the atmosphere. And green hydrogen fit a renewable heavy system because it's avoid life cycle emission and reduce import dependence. That is very important. Here on the right side, you can see the color of hydrogen, and you can see the process by they are produced. And then you see the carbon dioxide emission. Full red circle, it means the highest level of carbon dioxide emission. Environmental impact, again, if it's a full circle, then it's badly affecting the environment. And cleanliness level, if it is full circle, then it is clean. So you see the first four bad one. When we are producing hydrogen from the coal or natural gas without carbon capture and with carbon capture. So these are the brown, black, and blue. And then comes electrolysis or green hydrogen. So these yellow, pink, and green, they all comes in under green normal, common category. But specifically with nuclear power plant, if you are using electricity, then it is the pink one. And if you are using solar power, then it is yellow one. And if you are using other renewable energy sources, then it is green one. We need not to forget that hydrogen is also available as a element, stored element inside the earth. So, and that is the white hydrogen. There are some established technologies for producing the green hydrogen, and alkaline electrolyzer, proton exchange membrane electrolyzer, and solid oxide electrolyzer. These are the three common technologies. And this efficiency of these electrolyzers, they are ranging between 60 to 82%. I was fortunate to contribute for the Europe first 20 megawatt electrolyzer plant in Fredericia, which was built by my previous company, Above Fuel, which is now productive and supplying green hydrogen to the Flensburg, Germany. Here you can see that what are the requirements for these electrolyzers. So specifically, solid oxide and proton membrane exchange electrolyzers, they need stable power supply. And then membrane electrode assembly, that is specifically for proton exchange membrane, is very sensitive for impurity. And temperature wise, we can say that mostly they are working below 100 degrees centigrade, but solid oxide, that's temperature range is 700 to 1000 degree. And there it's having added advantage that it can work with not only electricity, but with the excess heat. So biomass can feed into the solid oxide electrolyzer, and in case of renewable energy fluctuation, this biomass can provide the heat, and then efficiency can be maintained, and steady state operation of solid oxide fuel electrolyzer can be maintained. Here I try to give you a glimpse how it works. So in alkaline electrolyzer hydroxide ion, they are moving through membrane, and in proton exchange membrane, that's proton H plus, as you know, this tiny proton, that's moving. And in solid oxide, that's through ceramics material, oxygen ion is moving. These are the some companies which are producing electrolyzers. Please note that all development in electrolyzer production, that is a story of last 5 years. And it is not the case that electrolyzer is a new thing. Null hydrogen in Norway, they are building these electrolyzers from last century, more than 100 years. But there were only few buyers. Earlier, this petrochemical industry and pharmacy, they were using the purest form of hydrogen, so they were using electrolyzer. But now, due to this green energy transition. Electrolyzer is backbone for whole world, and there are not less than 100 players right around Europe. They are working on these technologies. You see the name here, and they are working on all three type of technology: alkaline, PEM, and SOEC. Whereas alkaline is having right now major portion, and in future SOEC is having promises. So if we talk about energy conversion chain, electricity entered the electrolyzer, hydrogen exists and it compressed, hydrogen is stored, and this hydrogen is later converted through fuel cell or turbine. And round trip efficiency is about 30 to 40%. That is the drawback, because electrolyzer is having its own efficiency 60 to 80%, and again fuel cell is again having the same range of efficiency. So round trip efficiency is around 30 to 40%. So it is not advisable that you produce green hydrogen and then you reconvert it to electricity. Good design reduces losses by optimizing compression and storage pressure as well as end use selection. Here you see energy conversion chain on the right side. You see the leftmost part, that's the renewable energy sources. In between, you are having electrolyzer, and here this electrolyzer needed a pure water. That is also an extra requirement. For 1 kg of hydrogen production, you need around 18 liter of pure water. And then this hydrogen can be fed into fuel cell, and that can be used in aviation or in marine sector or in heavy duty trucks or in light passenger vehicle. When we are talking about fuel cell for aviation and marine sector, then it is a liquid fuel and it is a e-methanol or e-ammonia. That is the byproduct of green hydrogen. It can fed to production of pharmaceutical substance. It can be fed to power to gas. So we convert this green hydrogen to gaseous form, and then gas. This hydrogen is used for the district heating and other uses, and it can be used as a energy storage too. So as I promised you, I will move it to intelligent and efficient power electronics for green hydrogen production. Here you can see that this is the electrolyzer plant, and with the red number, you can see the efficiency of those particular parts. So there is a power supply, there is electrolyzer, and then there is a auxiliary circuit which for gas separation, for deoxidation, as well as for feeding the water. So all in all, if you combine all those efficiency, then you will find that overall efficiency is between 60 to 80%. So here you see that this 15%, 10 to 15% losses in power supply, that can be very well taken care by power electronics, improved power electronics, as well as for compression and for feeding the water. That circuit is also controlled by the power electronics, and there also we can see a substantial improvement by using IE4 and IE5 motors and efficient silicon carbide power stack. We can increase the efficiency of this conversion further. So we can use solar inverters, and we can use DC optimizer, means DC-DC converters, to match the voltage rating. We can use wind turbine converter, because yesterday wind is today's fuel, and we can convert the wind particles to hydrogen molecule, and this is the cheapest form of energy source. Then we are having this EV charger and motor drive. There also we contribute a lot by having intelligent power electronics, converter for batteries and electrolyzers that I already mentioned here. and from classical to intelligent power converter. So it means we are having, instead of classical fixed control and limiting sensing converter, we are having intelligent converter, which are rich in sensing. They are having equipped with onboard diagnostic and connectivity. They are having a adaptive control feature, condition monitoring, and cyber secure communication. And benefit is high efficiency, reduced downtime, and longer life. Use cases, intelligent converter in solar and wind park, small MPPT, grid support function, and voltage and frequency support. And they curtailment minimizes by better forecasting and control. And fleet level view and supervision can be done by a single unit. How much time I'm having still?
Sir, you have to conclude by 12:05.
So, well, sir, you may have take 5-10 minutes extra as there was a power failure. So, to compensate for that, you can take, sir.
So I will not go through deep power electronics because our forum is mixed forum and we are
Yes, sir.
more on from mechanical side. So I will
Exactly.
go through the more emphasizes part which is applicable for everybody.
Yes, sir.
So
Thank you.
let's talk about
Thank you, sir. This is.
So as I told, why a green hydrogen, this energy transition is needed and green hydrogen is needed. So marine sector, you cannot decarbonize this sector without hydrogen. So forget, batteries never will solve the purpose because their weight and their cost characteristics and their environmental bad effect. And ammonia, that is a byproduct of green hydrogen. So that works well for the for this marine sector. So then you see that if we want to decarbonize, and this marine sector is having around 20% of total decarbonization in the environment, world environment. So it is a huge culprit, as well as synthetic fuel that serve for aviation. We cannot use battery-driven planes. We need to use this synthetic fuel. That is again e-methanol or e-ammonia. That is produced by green hydrogen. And liquid hydrogen can support short to medium aircraft. We are having India is specifically having very good experience using this liquid hydrogen in our space mission. So that is we need to downsize or down apply in lower end market, and here we can see that we can lead the world this liquid hydrogen to support short to medium aircraft. Nobody talk about it, but here we are having great potential. Port plant bunkering terminals for green ammonia. That is also for the shipping sector we can do. And then comes economic factor. So if we see cost of hydrogen production, presently it is around $4 for gray hydrogen and far more than $4 for green hydrogen. Because of gray hydrogen, we are working on this technology from last century, and we are having centuries experience. Industry is used to produce this gray hydrogen. Green hydrogen is something where we are struggling with the efficiency of electrolyzers. Work is going on, and expectation is by 2030, green hydrogen cost will be between $1 to $2 per kg. And further, carbon pricing model that can be that European Union already implemented, that can help to implement and bringing the cost of green hydrogen further down. So if we break down the cost, then it comprises of electrolyzer investment. That is one of the biggest investment. Then power cast, water treatment, compression and storage, transport, and fuel cell or industrial process. So all in all, we can see this is the breakage of cost, and this is the current levelized cost of hydrogen. Further, we see the improvement in coming year due to the reduction due to fall in electrolyzer price, then reduction due to improvement in electrolyzer efficiency, further to renewable energy price, and further to change in operating expenditure, and benefit of direct production incentives. So this all in all, it's by 2030, what is predicted, this costs around $2. So what is the Bharat position? We are fortunate. We are having highest solar irradiation, and we are in the countries which are very benefited with the solar energy. We do have good wind belt from Tamil Nadu to Gujarat coastal area. We are having large fertilizer industry demand. So we are having demand inside the country, as well as we are our government of India is also giving incentive and accelerating the adoption. We have seen in Green Hydrogen India Summit 2024, commitment and guidelines from our respected Prime Minister. India policy framework, they say that production link incentive, green hydrogen purchase obligations, open access rule for electrolyzer and hydrogen hub development. So this is the vision for 2030, 5 million metric ton per annum production capacity, 125 gigawatt renewable energy capacity addition, 6 lakh full-time job, and CO2 emission expected to be averted by 50 million metric ton per annum. And this investment is around huge investment, 8 lakh crore plus. So what are the identified regions in Bharat for green hydrogen production? So we know that solar peaks in day, wind peaks at night or winter. So hybrid system can give you more stable electricity. Offshore wind offer strong and consistent wind. High capacity factor means more hours for electrolyzer operation, and more hour means cheap and higher hydrogen per year. A solar gives cheap daytime energy. It's helped reduce the average electricity price to the electrolyzer. So the thought for using either of the renewable energy sources, this is not practical. We need to use different type of renewable energy sources, and using a hybrid model of that will bring down the price of green. Battery storage, that is not a solution, but it can help you to absorb fast changes in wind and solar. And it also help you for grid forming purpose. So because you always have some electrical power in your control, which can be used to stabilize the grid in case of emergency. Here you see the green area. This is the map taken from the government of power ministry side, and these are the green area which were identified for green hydrogen production. Here you see this global trend, and you see this red color is where we see the promising cost of hydrogen, close to $1 to $2. So we see that India comes in that region, and we are very fortunate. So that is the future fuel. And only thing is, we need to have our own indigenous solution for electrolyzer, for hydrogen compression and hydrogen distribution and utilization. And there we need to work on full value chain of the hydrogen. We have already our major MNCs, they already started committed for green hydrogen production. So here are the numbers that our fossil fuel-based companies, they are moving to taking lead on the green hydrogen production. This is some recent news around the India, which is focused on the green hydrogen. A lot of things is happening. Denmark position. Denmark, no doubt that they are having very strong offshore wind production capability, because they were the inventor in 1990 for the offshore wind. and they are having multi-gigawatt plants around UK, around Denmark, around Norway, and they are building around 5 gigawatt cluster in Boston, close to Boston, and other part of world. Hydrogen pipeline to Germany that is already planned, and they are having high ambition for export to P2X solution. Here you can see this P2X, power to X, that is the term generated from this Denmark. Here they talk about renewable energy, that is your power, and that can be converted to X, and that X is electricity. This X is your green hydrogen, this X is your heat, or this X is your stored energy, or this X is your synthetic fuel. So you can store the energy in X form, and most important ingredient of this X is the green hydrogen. So what is required to make Bharat Atmanirbhar? For policymakers, support pilot that combine converter, digital twin and hydrogen. For industry, invest in digital competence on top of hardware. For academia, for us, design curricula that blend power electronics control and data science. And for student, we need to focus on skill in modeling, embedded control and cloud analytics. I would like to conclude my speech by saying energy transition require smart hardware plus smart software. Intelligent converter and digital twin reduce cost and risk. Hydrogen gives flexibility to integrate large share of renewable, and Atmanirbhar Bharat is achievable through focus R&D, manufacturing and talent development. So I wrote contributed in previous companies with this hydrogen patent, and a book is coming in IEEE press next first quarter next year, where I try to summarize my knowledge in hydrogen technologies. So this is in press. Being said that, thank you so much for your patience, and now forum is open for any question or any feedback or any suggestion.
Professor, what do you mean by gray hydrogen? How do you rate gray hydrogen with green hydrogen?
Gray hydrogen, you see, hydrogen are backbone for petrochemical industries and fertilizer industries, and they are produced through either natural gas or coal. So when they are produced by chemical synthesis of natural gas, then they are gray hydrogen. And black, when when coal is used, steam reformation technique, then that is black. And when you are using renewable energy, then a journal classification, we say that green hydrogen. Hydrogen is same, but it is produced by different method.
Methodologies are different. Starting materials are different.
Yes.
Okay, thank you.
So one question is from my side. Well, I am not very well versed in the hydrogen production so far as electrolysis system is concerned. When I was working in industry, there was one ammonia cracking plant which used to separate nitrogen and hydrogen. So, are there any means to get hydrogen with the use of renewable energy from any other compound which make use of hydrogen, which is where the hydrogen is one of the content?
See, this is the most simplest method, this water electrolysis. And it's the simplest thing. So if we are going for other chemical material and then we are aiming with the electrolysis, then that is not a viable solution. However, this in algae, this green algae based hydrogen production, that is a new technique, and biotechnology can help us. Yeah, that is also promising, but there is no industry scale or commercial scale solution developed so far. But there is one also one research group is trying to use the photosynthesis and use a special type of, you know, algae and other material which directly decompose and give hydrogen. But this is only pilot scale and research scale. They are not having any promising solution yet.
Thank you, sir.
Thank you, sir, for your insightful keynote address on crucial topic, accelerating the green transition for Atmanirbhar Bharat through intelligent powered converters, digital twins, and hydrogen integration. Let's move forward. The International Conference on ICRA-DMM to 2025 has received huge response from various reputed academics and research institutions across the globe. Over 162 papers has been received and 74 papers has been selected on the basis of high quality and application by the review committee and has been shortlisted for the publication in the form of e-souvenirs. We now invite all dignitaries and members of the technical program committee to join us virtually for official release of the conference e-souvenirs.
Thank you, all the dignitaries and conveners. Moving forward, let me introduce our next keynote speaker, Dr. P.K. Jain sir from IIITDM Jabalpur and also principal at RJIT Deganpur, BSF Academy, Gwalior. We are honored to introduce Sir as an eminent academician and accomplished researcher in the field of additive manufacturing and rapid prototyping, CNC machining, computational geometry, and CAD-CAM integration. He is currently serving as the principal of Rustomjee Institute of Technology, BSF Academy, Dekanpur, and is also a professor at PDPM, IIITDM, Jabalpur. Professor Jain has an exceptional research record with more than 72 SCI Index journal papers, 23 Scopus Index journal publications, 85 international conference papers, 38 book chapters, and over 3,600 citations with an H index of 32. He has guided 10 PhD scholars and 28 MTech dissertations. He has successfully handled several major sponsored research projects, including DST funded and IMprint India funded projects, with project grant exceeding 30 millions in total. His innovative contributions also include advancements in metal additive manufacturing and integrated RP systems. A respected academic leader, he has held key administrative roles such as Dean Students, Dean RSPC, Head of Mechanical Engineering Discipline, Member of the Board of Governors at IIITDM Jabalpur, and Chairman of the Placement Cell. May I now request Dr. Jain sir to deliver the keynote address. Sir, please.
It may take some seconds
Just to
join
update,
Dr.
due
PK
to
Jain
some
because
technical issue,
he has got some technical issue.
sir has got disconnected. So we are just trying to connect, sir. I think Dr. Jain sir has joined us. Sir, you are with us?
Yes, very much. Good morning, Professor Tomar. Good morning, Professor Kaushik. Yeah, good morning, Professor Tomar. Good morning, Professor Kaushik.
Good morning. Welcome to MIT University Madhya Pradesh virtually.
Thank you, sir. Thank you. Yeah, I visited many times your campus, sir. This beautiful campus.
So very good morning, sir, and we request you to please deliver the keynote address, sir, please.
Professor Jan, you can share your slides and then please go ahead.
Yes, yes. Nishita, you can see my screen?
Not yet. Yes, it's now you can go on slideshow and then go ahead.
Can you see it in the slideshow?
Yes, it's visible now. Please, fine.
So thank you, everyone, dignitaries available here and the participants. I was very much excited while seeing the topic of the conference on advances in design, materials, and manufacturing. So I have tried to briefly cover up in half an hour in all three aspects, which we have currently taken up research at IIIT Jabalpur in the area of additive manufacturing processes. So can I see the yeah, 63. Okay. So I would like to talk about the additive manufacturing, which I have chosen in the keyword in this talk title, novel induction heating assisted additive manufacturing technologies. So briefly, I would talk on the additive manufacturing processes. Currently, most of us use that 3D printer available in almost each of us in lab that is based on the polymer based, right? Then another I would like to talk again on the polymer based, but the material is in the powder form. So that would be on the material aspect. Then I will take you to how we have converted a CNC milling machine into a 3D printer and to work both on the additive and subtractive aspects on the same machine. So we can remove the material, we can add the material on the same build platform. And then we have developed the aluminum printing machine that is currently under development, that is under DST sponsored project. So I would like to share that as well with the participants of this conference. So let us begin with this additive manufacturing. What we take up as a additive manufacturing, where additive itself says something which is additive. So we are adding something, some material, and when it comes to manufacturing or the production or any product or fabrication approaches, immediate thing is comes in our mind is the machining. What we do in the machining? We remove the material. We have the stock and we remove the material. And another common thing is the joining. As we know, most of the fabrication we do with the welding processes or soldering processes. Another thing is very common for manufacturing, like injection molding, die casting. So we have this process, right? Now, today, what we are talking it, instead of removing material, or joining material, or shaping the material, we are talking about the deposition of the material. So see in the first figure on the left hand side, we were removing the material. So we have started from top to bottom. We have carefully removed the material. But in this process, what we are supposed to do, we are depositing the material from bottom to top. That is what initially, when this process started in early 1890s, that it is known as the layer deposition. That name comes rapid prototyping. Then the finally name, well accepted name came standardized name as the additive manufacturing, where we are doing the manufacturing not only the polymers but for the metals as well, right? So also some people now call it a 3D printing, because the printing is in 2D aspect, and when we say 3D printing, we are printing something which is three-dimensional. Okay, so that is what. Now, what the advantage we got in this additive manufacturing process, right? That creates a model of an object directly from the CAD model. In between, for mechanical aspects, patterns, dies, or tools, we don't require, right? So that is what we say, directly printing from a CAD model and deposit the material in a form of layer. And these layer thickness plays a crucial role that we will cover. So you can see here, that is a handle of the hair dryer gun. Okay, that hair dryer gun. Otherwise, you see, initially the rapid prototyping, when I was doing my PhD at IIT Delhi in 2005, we used to this rapid prototyping as a communication tool only, right? So what we used to say, communicate our design ideas among our peers, team members, our manufacturing engineers, or whosoever we want. So you see here, if without going for 3D printing, if we try to manufacture this complaint, the complexity of the die required for molding of this component, the number of cross-sectional views are required to communicate this design idea to others, right? So that is what we have started with we have for the additive manufacturing advantage. Another thing, you see, what we say here, the additive and subtractive both cases, right? So look at this here, what we do, we machining, right? So subtractive process, begin with a solid piece of work. Okay, now careful material removal is done, but the process may be very complex, exhaustive, time consuming, and expensive. And even sometimes the part may not be even able to build. Because of this, even if you have many people also say, why not with the 5-axis machining we can do that, right? But look at this here. Here in this case, you will have these intricate parts. Here your 5-axis CNC machining tool even cannot reach up to this point, right? So what we have the additive manufacturing process, where here in this case that I am talking on fuse deposition modeling process. Okay, so in this FDM process, what happens? We have the part material, we have the support material, and we deposit the material in a layer-wise fashion. So we start from the bottom to top. We deposit the material here, and we continue to have the material here in this case, right? So we will start material deposition from bottom to top. That is what we do in the additive manufacturing process. And here, what the advantage we got? We get the advantage that complexity of the part is no more a limitation, right? For any manufacturing process, constraint is what is the complexity of the part, right? Now here, whatever you can think, whatever you can design, whatever you can model, you can print it as it is. That's the beauty. And why we call it that the communication is start with a picture. So you see, nobody would like to write a paragraph to describe something. But instead of writing a paragraph or describing something in a text mode, somebody would like to say draw. Suppose I ask you we want to make a almirah. So instead of writing that 3x6 almirah, we will immediately draw something and show to the carpenter. We want this almirah, like, so that is the beauty of a picture for a communication purpose. So we often say a picture is worth 1,000 words, right? And now see, with the additive manufacturing, we have a model. So picture is 1,000 words. That model is again worth 1,000 pictures. That the advantage we got with the additive manufacturing or 3D printing. Now it is more established term known as the additive manufacturing, right? So see here some other examples. You can see here the colored model of the heart. The human anatomy you can directly print. The fully functional springs you can see. The temple model you can see. The engine blocks you can see. The ties you can see. That is the reason with the advent of the additive manufacturing processes, now the product development cycle becomes so compact. Now people do not take months to launch a product in the market. The product development, product design phase, and its various other manufacturing parts has become so certain that very quickly you can generate and develop the product, launch into the market. That is with the concurrent engineering, or you can say parallel engineering. Many things are available now, the different simulation tools, finite element tools, then packaging, etc., marketing, etc. You can proceed with the parallel way. So this the advantage we got with the additive manufacturing. So we have covered the additive manufacturing. Now I would like to talk about two additive manufacturing processes, right? They are commercially available. Many of you might be aware of it, but still I'm talking about the FDM and SLS process so that you can understand the importance of what I'm talking today, the new technology, which is the combination of FDM as well as SLS process as well as the energy sources, right? So if participants allow, you can say that what FDM about you know, right? The material is ABS process and the energy source is the resistance heating. So you can look at this on this. The process is solid based, support structure weak and capable of handle wide variety. Now look at this. What we do here. So before I explain, let me run this video first. Nishita, can you listen the voice of this video also, or I will explain?
No, it's getting distracted, so you can explain.
Yeah. Yes, sir.
Professor Jain, the voice is not very clear.
Yeah, voice I will explain. You see the model is available on the screen. That's the aeroplane model oriented properly in a vertical direction, right? So that in the minimum area we can fit it. Okay. Now look at this. Then what the software is doing right now, it is obtaining the cross section so that this aeroplane model will be available in a cross sectional layers, right? So every layer means this 3D model is now again converted in a number of 2D slices. Okay. Now these slices are there, so we will find out which slices are overhanging. For those overhanging slices, we require to provide the support. Okay. So look at this again. Right? You see here, that's the support generated. Right? This is the red color geometric model is there. Then the blue color is the support generated. Then every contour information, we have to generate the nozzle path where the material will be deposited. Look at this, every cross section, like your CT scan images, MRI images. Now, what is happening here? We are generating the 2D cross sectional nozzle path, in which area the material will be deposited. Right? This you can see here, the nozzles are now depositing the material. Right? The contour information generated, nozzle path generated. Now from this machine, the nozzle is depositing the ABS material. You can see here, I have paused so that you can see here that the model is ready, right? That is what we do with the FDM process. Now look at this. what we do in this additive processes. So before, for time constraint, I have first run the video so that you can quickly find out two wire material is there, right? One is the support filament, one is the material filament, right? Here is the red color, extruded heaters are there, right? And there are rollers. So these roller will push this material and deposit. So here the part material will be deposited. Here the support material will deposit to support this overhanging feature, right? And this is the elevator platform. So after one layer deposited, this elevator platform will go down every time. Here, the layer thickness is kept 150 micron or 200 micron, depending on the requirement, right? So that is what we take here. Now see here, the kind of model you can get with the 3D printing. The architectural model is shown over here. Then you can see here, the boiler model is shown here. The big size models you can print for education purpose as well as the fully functional use, right? So that is what we do in the additive. The key word I would like to take further for slide, that material is in the polymer form, material is in the wired spool form, and deposition takes place on the build platform, right? So on the build platform, every time it is going down, but heating source is the resistance heating, right? Now I'm coming to the select. If any question is there in the meantime, you may please type in the chat box. I will take it. Okay. Now I'm coming to the SLS process. What was there in the previous form? The material is in the form of wired form. So you are depositing like this. But now in this case, the same polymer material, nylon tall material, commercially known as PA2200 material, this is in the form of powder. Right? Now see in the center, you can see here, there is a beam expander, laser beam. Then this is the scanner, galvano scanner is there. Lenses are there. And here the recoater is there. So the powder material filled here, both the places, their recoater. This is the build chamber inside. This completely is build chamber. This is the unsintered powder. That is the part you are going to build. How you are going to build this part? See here in the first figure. This yellow color is the powder. So 40 to 60 micron size powder particles are there. We sprayed this powder, recoater. So this recoater will spray this powder on this build platform. Okay. Now, once this build platform is ready with the first layer thickness, the layer thickness is say 150 micron. Okay. Now the laser comes into the picture. And within this, you see here, these are the infrared heaters are there. So what we do, why we call it sintering, because this powder material is not at all going to melt. This will be sintered just below the melting temperature of the material. So the neck formation will be there and the two particles will be there, and these two particles will join due to the neck formation, right? Like this. So they will join with the heat applied, and these infrared heaters will keep this preheated. So say, for example, this polymer melting temperature is 180 degrees centigrade. Okay. So the preheating will be done up to say 170. Remaining 4 or 5 degrees centigrade up to say 175 degree will be provided with this laser. So what will happen? These particles will join with each other without melting. And once this platform, then this joining will done. So you can see over here, this corner, this part material is deposited. Okay. Here, that the solid material you can see over here. Now, once this is deposited, this platform will go down. Right? This platform will go one further down. Then this recoater will come and again spread the powder. So the cycle will goes on, and there is some pre-melting also for the previous layer, so that both the layers will join together. Okay. Now look at this. What we do? Powder base, support structure not required. Why this required in the previous case? Because the material is available in the solid form. So suppose you have this overhanging part, this part required support. But here you don't require support because here the powder material is already there. Right? So here powder will become solid, but here powder will be there. Na? So this powder will provide support to this overhanging feature that we will see in this video as well. Can you see the spare light? Can you see this light on this? right? That is basically the laser light which is coming on the polymer material. Normally it is absorbed, so you cannot see the reflection, but this video I have captured because we were doing this experiment with some nano clay. So because of the nano clay, the laser has become reflective. And you can see over here in this area, you can find out this the dense part you can see. That is the solid part. Now I'm coming to the material part, which is very much topic of this conference. I hope many of the paper related to material. You see here, this material characteristics, what you require. You require that at 175 or 176, this material should not be melt. But at 180 degree, it is melt. And 174 degree or 172 degree, the material will remain unaffected. Just within 2 to 5 degree temperature rise, it becomes solid. So you see here this tensile specimen printed on this specimen, right? So outside powder material is unsintered, that you can remove and reuse, and here this much becomes solid material. Okay, let's continue with this video. See here. See, this solidification is going on with the laser effect. And you see outside, you can see there is a light. This light is coming because of the infrared heaters. You see, the platform goes down and this recoater has sprayed a new layer of the powder on the build platform. Then again, this infrared heaters is switched on to heat the newly generated powder layer. Then again, laser will come only in the selected areas. That's why we call selective laser sintering, right? So we are talking about two processes. Okay. See here how the selective laser sintering will allow us to make this kind of part, right? Now, what is happening, the current status of this polymer additive manufacturing process, this has reached to the metal. Here, the powder particle size is 40 to 60 micron. Here, you can see the powder particle size is the 20 micron, and that you can see it is a steel. Stainless steel 316L material is there, and you see if we do not go for the manufacturing. Conference is mostly focused on the manufacturing, so you can look at this, how you are going to manufacture this component. Look at this. No CNC machine can produce this part. You can see here inside how the complicated things are there. Neither if you see how many parts you are going to manufacture the die and then join the die for casting of this material, right? This component. You see here how typical. This is the jet engine parts are there. The Wipro is using them. So look at this, how many extended components are there. So the normal machining even cannot manufacture these type of components, or it may be very, very typical, or you have to manufacture these components, several parts, and then weld them, join them, and do a lot of machining, right? That is what additive manufacturing allowing you to fabricate this part directly. How? Just in the powder form, the video I have shown you that the material will be printed in each and every layer. In fact, on this part, you can identify, you can see closely. I am zooming. You can also further zoom your screen and you can see over here, you can find out the layers. The waviness You can easily find out here layer is there, right? Now look at this, these two technologies we have tried to club. What is the difficulty up to this stage? Okay, Professor Kosik, I think I may have another 10 minutes, right?
Yes, you please.
Okay,
Go
so
ahead. Go ahead.
so
Go ahead in 10 minutes because the talk is very interesting and then informative.
okay, okay, thank you, sir. Let's see what we have tried, and I thought this topic to be discussed at this conference because it is exactly focusing on the design, materials, and manufacturing. So you see what kind of challenges are basically to be handled by engineers at this moment for the material requirement, right? Earlier you can say you melt some material and you done the casting, so you are talking about draft angle, etc., casting, pouring, dendrites, many things, right? Now see, you the same material you want in a powder form, so you have to do the pulverization, produce the powder in 20 to 30 micron size, and then the characteristics of the powder, so it should join. Now see here, in the polymer case, the unsintered powder can be reused, but in the metal case, unsintered powder cannot be reused. You look at this, when you apply this energy on the polymer bed, no warpage is occurring. You see what kind of parameter setting and materials are required. And the other side, you remember the papad. पापड़ सबको याद होगा, आप उसको बेक करिए गैस चूल्हे के ऊपर, क्या शेप देता है थोड़ा सा हीट देने के बाद. So you see what is happened for the thermal heat dissipation, right? Same पापड़ को आप जो है तेल की कढ़ाई में डाल दीजिए, you will get a
Uniform.
different, right? And same पापड़ आप लेके जाइए माइक्रोवेव ओवन में, right? What's the theory behind it? It's all the mechanical, the manufacturing, the thermal characteristics of the materials, how it is going to be fabricated. So these two process, polymer process, are well established, what I talked, right? Now from here we have to understand how this can be taken further. So what happens in the polymer material, we found that we are depending on the powder material to be available in the wired spool, which is providing you the additional cast point. So material you have, first you have to melt it and correct into the spool form. So we have developed this CNC machine, and in fact the CNC machine are already there, but what we have done, we have designed here an extruder head. Right? So you can see over here on this machine, on this Okuma machine, you can see over here, there is a extruder head. So we have designed this extruder head. In the left side, you can see this is the extruder head. Here we put the resistance heater. So this resistance heater will heat this nozzle, right? Here is the hopper. Now what the advantage in this, now material is no longer in the wired form. We can put the pellet material. आपके पास एक पुराना बाल्टी है, आप उसको क्रश कर दीजिए और क्रश करके इसके अंदर डाल दीजिए. Now this nozzle, here is the arbor screw. So that arbor screw will rotate at 50 rpm and push the material through this nozzle, right? From this nozzle, it is extruded, right? And then when it is extruded, the positioning system of the CNC machine is already utilized. So we can rotate, move this table and deposit the material. Let me run this video so that we can have a look. On the screen also, you can see in this picture, I have put the front view of the image. The material deposition takes place. And today with the time constraint, I am not talking about what kind of programming skills are required to achieve all these things. Now you can see this nozzle is depositing the material. See, just like your Mehendi cone, it is able. Now see how much synchronization, optimization, parameter setting is required. So you can see, this is the ABS material. So you have seen that how we are able to deposit the material on this CNC machine itself, right? This picture is more clear. You can see it. So outside contour is there, inside filling is there. Like what in the very first video I have shown you. These things, many people will say the software is available, but we never rely any external software, outsourced software. We have done all this programming, generated the G&M code. So this is on the same CNC machine. We are able to first deposit the material, and now we are removing the material. You can see here the same extruder head is changed. It is just like a tool changer. So we have changed that tool changer, and on the same CNC machine, now the milling cutter is installed. So that cutter is removing the unwanted material from the same deposited material. So the question may be like that, why it is machining in a triangular form, but we will leave this question for some other session. We are working with STL file, so everything is in a triangulated manner for this. Okay. So look at this, on the same setup, we are able to deposit the material. We will remove the material. That has allow us to develop in hybrid additive manufacturing. Then through the MATLAB programming, we have developed this graphical user interface to develop the program. So you can decide the road width, you can give the layer thickness, deposition speed, feed rate, etc. You can import an STL file, perform the slicing, toolpath generation, convert this whole information into the GMM code. So why GMM code? Because you wanted to send it to the CNC machine. Then show file. So you see this is STL file, contour, toolpath, everything is there. On the same graphical user interface, this will generate the program which will deposit the material from bottom to top. Same graphical user interface, it will generate the G&M code from top to bottom. So you can again give the parameter like cutting diameter, step over, tool path, GMN codes, etc. Okay, and you can see the file, and this tool path you can supply to your CNC machine. Now what happens? By indigenous development of this full experimental setup, this has allowed us to do a lot of synchronization, as well as this has allowed us to use this flexibly part fabrication. Right? In this machine, you cannot use the flexible material because wired spool is there, so it will bend. So that buckling to be avoided, we have the flexible, and then further, since we are on our own, so we can mix some other material to make it electrically conductive. This is another challenge I am discussing with all the participants of this conference, to get the flexible, at the same time electrical conductive, at the same time suitable for additive manufacturing. Right? So both the additive manufacturing suitability to be ensured. Right? So see here, we can develop on the same machine, print this kind of flexible parts. No 3D printing machine can build this kind of flexible parts. You see here, that is 3D printed. And I hope you understand why we want a 3D printed. Suppose you are working with the sensors, actuators, robotics, etc. You can wear some device in your hand and then you can operate. So look at this. This is the flexible part, 3D printed. Time constraint, I'm just moving ahead. So now this has allowed us to develop another 2-3 minutes, sir. 1 o'clock I will complete. So induction conduction based metal additive manufacturing. We have started with the polymers. I have chosen to talk on commercially available machines. See what commercial machines are using: the laser source, electron beam, and arc plasma for metal currently. Right now, what we are talking about, the induction heating. We all know the induction cooker, right? Induction heaters are always there, right? How fast it is. and how safe and clean it is, right? The same we are trying to apply with the additive manufacturing, which we have talked. At the same time, we are trying to eliminate the requirement of the powder form of the metal, so that very much cost can be saved, and you can eliminate that first step of making stainless steel available in a 20 micron size, right? So in this process, what we do, we have developed a lot of experimentation have done, but today we will take you directly to the aluminum printing. You see here, this video is showing you how we have taken the aluminum printing. See in this video, this is the induction heater. Heating coil is there, and inside there is a MS steel extruder head is there on the bottom side nozzle. So you can relate the first video I've shown you, commercial machine, the polymer machine. Now this is the indigenously made at IIITDM Jabalpur. This is one of the DST sponsored project, patented work is I'm showing here. So you can see here, this is depositing the aluminum at 600 degrees centigrade temperature, and within 60 seconds we reach the 600 degrees centigrade temperature. We can reach up to 1000 with this induction coil, but we restrict it through PID controller to only 600 degrees centigrade temperature for this aluminum to be deposited. Still, there is a lot of challenges. We cannot build the overhanging parts, which I shown in the SLS process. We cannot even build the joining of these parts to be ensured properly, which is still we are struggling. So you see, this is the aluminum printing. You see here, this is the full setup I am showing you, indigenous, the Mac 3 open source software. We use the induction heater, the full mechatronics control is there. This is the closed vacuum chamber. Inside this lot of positioning systems we use. Right? This is the positioning system. I can show you, so ball screws, that student and that researcher must do by their own. So we can supply the pulses to different stepper motors and control this part printing bed by our own controller software. Okay, this is the current printing of the part. This is also another glimpse of the aluminum printing. And this is the full setup you can see over here. This is first in the open environment. This is the wired spool. You see aluminum available in a wire form commercially. So we are not required anymore the powder of the metal, right? And see over here, this is the printing. And this multi-layer 3D printing, let me run. This is the inside within the closed chamber. We are able to print this part. See here, this is on the bottom side. This is again heated the part bed you can see here. On the top, it is depositing the aluminum material. And inside this, everything you can see the ball screw mechanism, etc. Okay. So I think with this we can close. These are the some other glimpses just, and then we can close. Some other videos of aluminum printing required not at this stage. So we can close the session.
Yes, Professor Prashant, I have some few clarification quick.
Yes, quickly. Please, welcome, sir.
You know, what has happened in case of conventional manufacturing, what we normally do is that we have to have a basic engineering design drawing, then detail engineering drawing, and then when the actual drawing goes on the floor for manufacturing, even then also there's some changes are there. Do you think the same process also takes place in additive manufacturing?
We can do, sir. That is always there. That we can say it's a part of design. So even in very much process chain of the additive manufacturing, also we consider the iterations. So if any iteration at the design, we can go back.
Okay. No, but what has happened is, for example, 3D printing, it's almost like frozen, and then there's no choice to make any changes at the floor. Once a 3D design has been given frozen.
No. Yes. On the floor, change is not possible, sir.
Not possible.
On the floor, not possible.
In case of conventional, it is possible.
You can say, sir, some component. But suppose you want to change any fillet radius, that is not possible. Some tolerances are not possible. So like this, here we consider this is a closed loop.
Close,
We
correct.
are
That's
printing
right.
up to this part, we are checking the final prototype, and you are testing. And if there is anything, then again redesign. That
Correct.
would be
So
always
anyhow,
there.
that has clarified. Another question which I was asking, you gave an example of a powder heating. For example, 180 degrees centigrade is there, 170, 175, and then within a 2-3 degrees centigrade it melts. But how does it uniformity is achieved? No doubt, from your examples you have given excellent talk. You have given different examples and the different parts you have already shown, which has come with very precision and very accuracy. But what kind of heating technologies are adopted which give the constant heating as well as thickness of the layer of with the particularly with the powder technology? Metal is perfectly alright, polymer is perfectly alright, but in case of powder, to have the uniform heating and then depositing additive manufacturing. So, what are the challenges you normally face, or what has been the challenges for powder technology in comparison to what you showed the aluminum wire which you have been replaced with the help of powder?
Perfectly well understood, sir. You have taken the gist of that, what I was trying to explain. That's the major, the research completely lies. You have described what the research required in this area. That the first thing, the uniform heating. So in the particular case of SLS, the uniform heating comes from the infrared heaters, and only 4-5 degrees centigrade come from the temperature. Another thing, we perform the differential scanning calorimetry analysis to understand the powder characteristics first before going for any 3D printing of the for SLS process.
Correct.
So
Correct.
what is the melting temperature? What is the crystallization temperature? And we call it sintering window. So that has to be very small.
Correct.
Like it can't happen कि एक बार मटेरियल मेल्ट हो गया, अब वो आधे घंटे तक सॉलिडिफिकेशन ही नहीं हो रहा है.
Correct. That's right. That has
So
the challenges.
that has to be very much taken care into that.
And my last question, you
Sir.
gave an example because material is very important for additive manufacturing. Process is same, but material is also equally important, which you have very much highlighted. And you gave an example of papad. Now the material is same, papad is same, but when you say that directly on flame, it gets deformated. When you put it in oil, it is uniform, and it's much better when you go for the microwave. So it is
Right.
basically this process or the mediums through which normally heating process takes place that only controls the shape, size. Otherwise,
Yes.
for example, deformation is taking place with the direct flame, and uniformity
Right.
is there with the oil
Yeah.
or the
Yes.
microwave.
Yes, you already taken up the answer of your question, sir, for the participants' benefit, that this is the uniformity, the same thing. Because when we are taking it to the flame, it's not at all there, because anyway, in only one area, heat is going there. So when the conduction starts, direct heating is not there, the deformation is coming. And the same happens not only in this, the same phenomena happen with the selective laser sintering also. Lot of
Correct.
parts are failed because of that. So there are again further limitation that how much size you can take. Suppose part bed is very high and uniform heating cannot be maintained. The deformation will take over here. And here what happens? The recorder is on the first layer, and suppose first layer is deformed and it lifted from its base. So it will be say 1 millimeter height. Then it will start moving with the recorder. So when there is no first layer, no second, no third layer, so that has to be very, very precisely managed.
Thank you
Otherwise,
so much for an excellent talk. It was very informative. Thank you so much. Thank you.
Thank you, Professor Kaushik.
Yeah, Professor Dr. Jain, Dr. Sanjeet has got one question.
Sir.
Sanjeet, sir, please, you can.
So, good afternoon,
Good
Dr.
morning, sir.
Good morning. It's a very delighted talk, and I learned a lot. And I have a question regarding this powder coating that way manufacturing some kind of magnet. I was talking to one of my friend in HAL Lucknow, and they were struggling with in situ magnetization of machine. So is it possible that we will have different kind of magnetic material, earth magnetic material and ferrite magnetic material, so that we do have different flux density in different layer? And by actual application, when we need higher flux density, then we can magnetize that layer. And when we need lower flux density, then we can demagnetize different layer. So different layer of permanent magnet material, rare earth magnet material, and then we develop that magnet in that way. Is there any work on that direction, or you have some thoughts on that?
Sir, very, very interesting future direction you have shown to us as well as all the participants also. In this, we use a lot of electrical magnetofaraday laws, etc., for this eddy current to get this induction heating. But I did not come across, we come across that functionally graded materials are there. So we can vary the density corresponding to the part strength as well in various mechanical materials. But really, I did not come across that we did not come across any such that where the varying magnetic density is achieved. But that may be very good idea, because here the powder material deposited each and every layer. Let us also explore if magnetic properties can also be varied.
See, why I ask you this, because you did a lot of work on mechatronics, and I have seen that stepper motor and other things you told.
Right.
And that is my research area. So you see example in electrical vehicle, we are running always inverter in deep field weakening. So our motor is magnetized, and when it's running to high speed region, then our inverter is unnecessarily putting negative D current. It is loaded in that direction also. And if you miss the control, then you can blow the inverter. But with this design, where you can program the magnetic property or magnet flux density, then in the high speed, you demagnetize it, and at the low speed, you take the full flux density. So, and your inverter will be accordingly more efficient, and your operation will be smooth. So maybe we'll connect
very
later
nice.
for this topic.
It can be explored further. The time-dependent magnetic effects, magnetization, demagnetization as per the requirement. That may be really very, very good aspect in EV.
We'll talk about it later. Okay, thank you so much. And once again, yeah.
Nandisha, you can conclude.
I would like to
Thank you, sir, for your insight.
Before you conclude, I would like to appreciate the nice lecture delivery by Dr. Jain. You really explained the future material here. And I have a suggestion in this, that while thinking of the materials, always think of biomaterials also. Because, if you see from a strength point of view, then one of the scientists have proved that a fiber of Spider-Man's web is stronger than the steel fiber.
Right.
So that kind of means, this is the time of multidisciplinary research, not transdisciplinary or simply the interdisciplinary. Because without that, you cannot innovate something new. So we should think beyond our boundaries. Because an engineer thinks from the boundary of engineering. A biologist thinks like I'm a biologist. I think always in the boundaries of biology. But there are many aspects which we should think beyond. So this is really a very good input by you. And as far as materials are concerned, I always quote one or other thing from the Indian knowledge system. And that is about the तुलसीदास ने कहा है कि सकल पदार्थ है जगमाही कर्म ही नर पावत नाही। जैन साहब सुनाया ना आपने ये? इसका मतलब है कि it is only up to us, we the scientist, if we explore the world, every kind of material is there. But how you can think of and how you can, the first thing is ideate. And ideate, then create, then innovate. So there are steps of research and innovation.
Right.
So
Very
we should
nice.
think from this angle also, that everything is there in this universe. Only thing is that we have to identify. There are many materials which have not yet identified, and if they're identified and used in a proper manner, then I think the existing materials can be replaced very easily. So looking to the B-1 bomber of the America, we think of why we can't create such kind of material by which our material can also become invisible and is better than that developed by US. So thank you very much once again, Dr. Jensam. This is only my suggestion.
Thank you, sir.
So thank you very much.
Thank you, sir, for your insightful and inspiring keynote address on the development of the novel induction heating assisted additive manufacturing technology. I would also like to thank Honorable Pro Vice Chancellor Research, Professor Dr. M.P. Kaushik, for joining us and gracing the conference with his esteemed presence. With that enriching and inspiring morning session, we now take break for the lunch. The parallel technical session will begin at the 2 p.m. in the online. Thank you everyone to join us in the inaugural session. Have a great day ahead.
Thank you all. Thank you very much.
Thank you.
Thank you.